Good evening. This is James Cook, Assistant Professor of Social Science at the University of Maine at Augusta, and we're here almost in week 13 of the Undergraduate Social Networks class of the University of Maine at Augusta. If you're taking this class for credit, fear not, you are very close to the end. What I want to show you today is the last step in what you need in terms of skill in order to carry out a multivariate, which just means more than one variable, analysis to explain variation in patterns of relations in a social network, to explain something about a social network. This is the big assignment that you have at the end of the semester, and you can do it. You have all the skills, save what I'm about to share with you in this relatively short video. And as I hope to explain to you, it's not all that complicated, especially if you've been paying attention in the weeks prior. Without further ado, we'll get started. So today we'll be talking about setting up and running a QAP regression. We've talked about what regression is. We've gone through a few examples, including at the beginning of this week, of interpreting regression coefficients and understanding what they mean. So now we just need to figure out what this QAP business is. It stands for Quadratic Assignment Procedure, but really what it means is that it is a regression in which the thing you're studying is not an individual outcome, but an outcome in a relationship between two people. The relationship is what makes it related to a network. So, to review from the example earlier in this lecture, in the text portion of the lecture, when we're talking about how many people are viewing videos within the past year in my YouTube channel, we could run a traditional regression. In a traditional regression, every case is in a row, every variable is in a column. So in this case, I've highlighted the case of Arkansas. It's a case because it's one of the things we're studying, one of the states. And that case has a number of observations. It has an observation for the variable geodesic distance to Maine. The geodesic distance to Maine of Arkansas is 8. You have to cross 8 borders in order to get from Arkansas to Maine. Arkansas has 2.916 million people in it. At least it did in 2010, which was the last available measuring date. It is not Maine, so we have a 0 there instead of a 1. 0 and 1 are how we measure dichotomous variables, variables that can take on two states. And there is one person from Arkansas who's viewed my videos in the last year. This is the traditional way, 11 out of 12 undergraduate classes, you will see information presented. Cases in rows and different variables in columns. It's all in one table. And if you're interested in running a regression, remember, is just trying to assess whether an independent variable, or in a multiple regression, more than one independent variable, is somehow associated with a dependent variable for a particular case across all of the cases. So here we would ask, is the geodesic distance to Maine somehow related to the fact that there's only one view of my videos in the last year from Arkansas, as opposed to 36 of them from California? Or is the fact that there are more in California due to the fact that there are many more people who live in California? 37 million. That's, more than 1 out of 10 people living in California in the entire United States. If that's the data structure for a traditional regression, the data structure for a QAP regression will look very different. Why? Because the data looks like a network. Because it does involve a network. A traditional regression describes behavior of individuals. QAP regression describes relationships in patterns. A traditional regression has each case as a row, but a QAP regression has a case being a cell of row I and column J. And corresponding cells across different matrices are your cases. The number of cases in a traditional regression is the same as the number of people that you're studying, or the number of states. Whatever the individual units are, the number of them is the number of cases. But the number of cases in a QAP regression is the same as the number of non-diagonal cells in the network. That means, going back to your definition of number of possible ties that you used to calculate density, that for a symmetric network, the number of cases is not the number of nodes, n, but it is n times n minus 1 divided by 2, a lot more cases. For asymmetric networks, in which there is no direction, like having lunch with, the number of cases equals n times n minus 1. Still, a whole lot of cases. In traditional regression, each variable is a column. But in QAP regression, each variable is measured using a different matrix, in which all matrices feature the same nodes but have different relations in the cells, representing a different idea. Each matrix represents a different idea about how the nodes could possibly relate to one another. So in a QAP regression, you're going to find a number of different matrices, all in a number of different files in your UCINET software. That is a lot more to keep track of than in a traditional regression, where all of your data can be found in one table, in one place that you can look at all at once. Let's boil that down to a practical example, okay? And let's make it in a really simple matrix of network data. We might have a dependent variable. Are some people friends? And let's just look at 3 people, Al, Betty, and Cleo. And you notice some zeros and ones, and by now you know what they mean. A 1 means, for Al and Betty, that Al and Betty are friends. Al is also friends with Cleo. Cleo and Betty are not friends, which is why there's a 0. And then there's a diagonal. And we're just entering those as zeros because that's non-meaningful information. We have independent variables then that contain the same nodes in them. Al and Betty are not the same gender. Al and Cleo are not the same gender. Betty and Cleo, however, are the same gender. And so there's a 1 there in the same gender matrix. Having shared gender is a commonality. It's a shared relationship to gender. Do 2 people go to the same church on Sundays? Al and Betty do, which is why they have a 1 in the matrix for same church. Cleo and Betty go to the same church. Al and Cleo do not go to the same church. How is that possible? Well, sometimes people go to more than one church. It looks like Al and Betty, when they go to church, are going to a different church than Betty and Cleo are going to. Okay, so they go to different churches in that case. Those are same gender and same church, independent variables that we might use to predict whether Al, Betty, and Cleo are friends. The friends is the dependent variable. It's the variable that we want to explain. And there is variation here. Not all of them are friends, and some of them are. There are 3 cases in this very simple example, because this is a symmetric network. So the number of possible ties is 3 times 2, n times n minus 1. 3 times 2 equals 6, divided by 2, which equals 3. And you can see that for yourself, that there are 3 possible ties here. And so there are 3 cases. The cases of Al and Betty, Al and Cleo, and Betty and Cleo. And the key is to recognize that the Al-Betty case spans across the matrices. Okay? And in fact, you could think of the corresponding cases as creating a row of data in a traditional data set. How would you go about, practically speaking, very practically speaking, generating multiple matrices to describe the kinds of data that I just showed you, multiple kinds of relations between the same nodes. How would you create matrices like that? Well, you've already created some matrices this semester, which is cool. You've done it many times. You should be somewhat familiar with it by now, but there are some tricks that I want to go through when you're starting with some data that are maybe sitting there in a Microsoft Excel file and waiting to be turned into network data, waiting to be turned into relations. Let's run through an example. I'm going to hop out of PowerPoint for a moment. And let's head over here to a somewhat larger example, one in which we have a traditional data set in which every column is a different variable and every row is a different case. Now we've collected this information about people. How could we take all of this information and possibly turn it into network data, into data about relations? The first thing we need to do is we need to do something called recoding some of the data. Remember that matrices are all about numbers, and there are some of these variables that don't have numbers in them. Now, there are a lot of columns here. There's a lot of information. We're going to work through it step by step, and we're going to work through it, most importantly, column by column. That's key. There's different kinds of information here, and if we all try to mash it all together, it won't really mean anything. I'm going to take this information, which I've put into a Microsoft Excel spreadsheet because it's a handy way to store it, and I'm going to copy it over to UCINET, step by step, one by one. But as I do that, I'm going to take some of this text information and I'm going to turn it into numbers. Okay, so let's work with that. Let's start with party. We have 13 individuals here, number 2 through number 14, Alice through May, and we're going to copy that information over here. But first, I said we have to turn party into numbers. Now, these are pretend legislators. Imagine we have a really small state legislature in which there are just 13 members of the legislature, and they're in the Democratic and Republican Party. There are no third-party members of the legislature in this example. We have D's and R's. Well, they're different. That's what's really important for us to know. So why don't we recode those to zeros and ones? And we can think of it as, let's make Republicans equal to 1. And the question is, are you a Republican or are you not? In which case you would be a Democrat. So zeros are going to be Democrats and ones are going to be R's. Now I'm going to show you a trick. If you select a column and you hit Control-H, that will bring up find and replace, and then you can replace D with 0, replace all, and then we can go and we can replace R's with ones. Now that might change party. Let's take a look. Oh, it did! It changed our label, so we're going to go back and retype that. Party. Now we're ready to take that information, copy it over, and start up UCINET. We're going to hit our spreadsheet editor key, and we're going to paste this in. Great. Now, let's make sure we have Alice through May. We have zeros and ones, and we are going to save that as, I'm going to call this FL for fake legislature party. FL party. Great. Now we've got party. What can we do with FL party? That's not yet network information. But we can turn that into network information by heading to data, and we could do one of two things. We could do affiliations, but if we do affiliations, let's look at that data structure again. FL party. Let's display that. And I want to show you something interesting, which is that if we think of this as affiliations, it's only describing who's in the Republican Party. It's not, if we take ones as being members of a club, it's not affirmatively saying someone is in the Democratic Party. How can we let the zeros and how can we let them be meaningful? Well, we can do that by using a different command, which is attribute to matrix. And we could look for exact matches. Let's do that. Let's go right through that. We're going to select the input attribute matrix, FL party, and we're going to make sure that we have selected the column for party. And then it's going to give us the FL party, same party output data matrix data set. That's fine. We're going to head and we're going to the method, and we're going to select the method exact matches. And it describes it down here. Look, if I change these, okay, it'll change the output data set name. Here, we're interested in exact matches. If there are two people who both have zeros, they're going to have the same attribute, and that's going to give them a value of 1. If two people, two other legislators, a pair of them both have 1s, that means they're both Republican, and we want to give them a 1. We want to have zeros be for when one person is a Democrat and one person is a Republican. Then they're not in the same party, and we want that to be a 0. We don't want any normalization. Don't do anything funny with it. And let's hit OK and see what happens. Perfect. Over here we can see Alice and Carl and Earl, who we know are in the same party from our prior look at that spreadsheet, are listed as in the same party. Bert and Donna, who are both Republicans, are listed as in the same party. So now I can write this down, and I know that we have a matrix, and it's called FL party. Okay, that was the input file. Okay, and I'll be able to look that one up and use that one later. Let's head back to the spreadsheet and take a look at our next. Our next column is one that's called sex. We could do the same thing as we did before. For party, we can say, well, let's make one of those sexes, female and male, equal to 1 and the other one equal to 0. And it'll now be, instead of just saying who's an F and who's an M, it'll be answering a question, let's say, who's an F? Who's a female? Let's select our column. Let's hit Control-H for replace. And then let's replace Fs with 1s. Replace all. And let's replace M's with 0s. Replace all. Now we've recoded it. We've done what matrices require, which is math, numbers, not letters, not text. And let's head back and let's open up our FL party. And now let's head in here and let's change that label to sex. And we're going to, actually, let's just copy that whole column. Whoa. Let's try to find that column there. Oh, there it is. Okay. Sometimes when you paste in, you will find that a column disappears. Head over to dimensions and describe again how many columns you want, and it'll show back up usually. Let's check through and make sure that we are actually measuring what we think we are. Alice has a feminine and a female score of 1. Bert and Carl and Earl and Gus and Luis and Jasper have 0s. They're men. Helga, Ingrid, Kate, and May are 1s. Frida is as well. This is what we expect. Now let's save this as FL fake legislature sex. And we can close that, and we can head over and we can do exactly the same thing we did before. We can go to data and attribute to matrix, And we're going to make sure that we don't use FL party, but we use FL sex. And we want exact matches, FL sex, same sex. That's very descriptive. Everything's going to start with FL. This is handy because that way we can find that it's all in the same place in our folder on our computer. The column that we're using is sex. I think we're ready to go. And let's see. Are Alice, Donna, Frida, Helga, Ingrid, Kate, and A on the Alice row? Are they all ones? Yes. For Bert, are all the ones on the row other males? Yes. Congratulations, we have a second matrix. Now we have two matrices. They describe the same nodes, but they describe a different relation between them. This is great at getting good. Let's head back over to our data sheet. And let's think about that next one, seat. Did you know that in some legislatures there are assigned seats, just like in second grade, school? It's true. And one of the things we know is that proximity leads to interaction. Is it possible that two people who have seats next to each other might interact with each other a little bit more often? Might they decide to do things together if they're like, desk mates? Sure, that's a possibility. So in our fake legislature, in which there are 13 seats for 13 people, we're going to go ahead and we're going to copy that right in. Now, that's already numerical information. So what can we do with that? We can head back over. We can open up FL sex. Oh, we could open up FL sex. Let's try that one more time. There we are. And we could paste in... disappearing, make it reappear, the seat numbers. That's exactly right. So what do we do with seat number? Well, first we save it. Let's call it FL seat. Okay, that's saved. And now we're going to head to attribute to matrix, data, attribute to matrix, but we're going to do something different. We want to know how far away people are in their seats. Well, fortunately, the seats in this case are listed in order. Let's imagine that chair number 1 is next to chair number 2. Chair number 2 is next to chair number 3. Chair number 3 is next to chair number 4, and so on. So if we were able to get the difference between the two, then we would know how far away in seats people were. You could think of this as a network distance, right? It's very hard to speak to someone who's 2 chairs away. It's a horizon of observability. Hello, Noah Friedkin, right? 3 chairs away, it's next to impossible. 4 chairs, you have to start sending messages. Great. We want to make sure that we do a calculation based on absolute difference, because otherwise, if we just did a numerical difference, then if 3 related to 2, that might be a negative distance, but 3 relating to 4 might be a positive distance. And we don't care which direction it goes in, left or right, positively or negatively. We just want to know what the distance is. And so to say absolute, it means that you take the absolute value of the difference. Okay, so this is going to be called FL sex. Oh, goodness, I almost did sex, didn't I? As the input attribute, always be careful, FL seat. This is why we always look at every option before we hit that big old K button. Yeah, we want seat number. Okay. And we want the absolute difference. This is the seat number. That's what they're working with. We're going to hit OK. I'm a little nervous because there's a number sign in here, and sometimes that confuses programs, but let's see what happens. It worked. Oh, and check that out. Okay. If you look at the results over here, you can see that as you move across the rows and people get farther away from one another, they get farther away from each other in terms of their seats. And so the numbers describing distance go up. Awesome. We have information about how far people are away from each other in their assigned seats in our fake legislature. It's another theory about what might lead people to do something. Well, what's our dependent variable? We haven't gotten there yet. But it has to be some kind of action. Why? Because that's what I want you to do for your final piece of work. Okay, we have another one. It's called FL seat. FL party, FL sex, and FL seat. I love it. This is great. Okay, let's keep going. What do we have over here? We've got birth year. Okay. Hello, homophily. Homophily says, going back to our second lecture, that was a long time ago, right? Homophily says people who are similar are more likely to associate with each other. Birds of a feather flock together. There are a couple of reasons why that might be, but one thing that we do know is that people who are similar in age to one another are more likely to interact with one another. Might that happen in a legislature? Let's find out. So let's take that birth year information. Let's head over here and open up FL seat. And we're going to copy in, paste in our new information. Oh, and let's make that column reappear. Birth year. There it is. I'm going to save this before I forget. FL birth year. Okay, this is when people were born. I think we also want absolute difference here. So because it doesn't matter who was born before, who was born after, unless you wanted to get into a really interesting theory about older people being in charge or younger people being in charge. Let's not do that one today. Let's just go to data and find out how distant people are in years of age. And if people are distant more in years of age, they're going to have a bigger age distance between them. And that's kind of like a network distance in a way. It means that people with a bigger distance are going to be less likely to interact if we believe homophily here. So let's use attribute to matrix, and let's use absolute difference. Let's pick the right variable. It's going to be called FL birth year. We want the absolute difference. Oh, and there we are. Okay, they're all whole numbers, which is good. They should be. And they describe differences in years. Awesome. Okay, and if we look at those in greater detail, we will see that those numbers are correct. They're all above 0. None of them are negative. Everybody on the diagonal is the same age that they are themselves. That makes sense. And you could actually go back and compare this to the data. I can tell you that it's correct just by looking at it. But we could look at it further if we really wanted to. Now we have FL birth year. I love it. We're really progressing here. Now, I've been at this for not long, 20 minutes? And I'm already most of the way toward taking my data and doing something meaningful with it. What do you mean most of the way, you say? Well, here comes another big set. And here, I'm going to copy over 1, 2, 3, 4, 5 columns all at once. Why? Because they're all columns. They're all committees. The Committee on the Budget, the Committee on Crime, the Committee on Ethics, Committee on Health, and the Rules Committee. And we have 1s and 0s already. They refer to membership in committees. So we're looking for a committee overlap matrix, a person-by-person matrix to describe, from Alice to May, all of them, who's on what committees with whom, and how many of them. Oh, I want to find out. So I'm copying that all. I don't have to make any transformations. It's all already described in numbers. And I'm going to head over here to our spreadsheet editor. Now, let's see if this works. If I take FL sex, say, and I try to paste this in, is it going to blow up? What's it going to do? I don't rightly know because they change the software all the time. Let's find out. Oh, it's in there. I love it. Just like that. Okay, so it's pasted in now. What's the next thing we have to do? Always save and make sure we get it named the right thing. Otherwise, we'll get confused. FL committees. I'll call it FL com. FL com. What am I doing? I am literally writing this down on a sheet of paper so that I remember what I did so I can look it up later. I'm going to even write down, oh, it's in my social networks folder so I can find it later. Because you know what? After you do enough of these, you'll find maybe they're all over the place. You lose them. You forget what was the name of it and what did they mean. Write it down. That's something that will help you out and keep you from tearing your hair out. when you stop, go to get a cup of coffee, come back to your computer, and find all of a sudden you forgot what you were doing. Write it down. FLCOM. Saved. Now we have to transform it. These are affiliations, my friend. 2-mode to 1-mode. So I'm going to head over and I'm going to look for FLCOM. And I want to, I can never remember, which I think I want to compare row by row, and I think that's what it means, but I'm not sure, so I'm always going to go over here to help. Row represents row by row matrix of overlaps. Yes, that's the one I want to do. Persons by persons, not committees by committees. Committees by committees would be interesting, but it's not the same as what I'm interested in doing, which is to create a set of matrices that have all the same nodes all the time, but different relations in them. Find out which relations matter more. Yeah. Okay. I'm getting excited. Okay. And what really will be exciting is when you're not working with a fake legislature, but a real one. You quite possibly will be examining aspects of the behavior of political systems, maybe a state legislature if you're doing politics, or in an online network, maybe a Twitter network, something that nobody's ever looked at before, a piece of information either about who's talking about some idea online or about who's trying to pass what kind of bill. You will be generating knowledge, new knowledge, important knowledge, the kind of thing you might shove in a newspaper article, for goodness sake. So, there's another use for social network analysis. You want to become a journalist someday? Use this, and you will come up with the most interesting reporting. Okay, enough chatter, because it looks like we have a good overlap matrix. There are some people who have no committees in common, some people who have one committee in common, and some people who have 2 committees in common. Donna and Kate, for instance, are on 2 committees together. Great. Don't show this message again. Don't you just love those pop-ups? Okay. So now we've got that. That's FLCOM. I've already written that down. We are almost done, my friends. But we are not quite done. Because we have some votes over here. And this is our dependent variable. Votes in the same way. And we have a bit of a complication. We want to create, in this case, one matrix. And this one matrix is going to describe the number of times that 2 members of the legislature voted the same way. Now, if we had one column with just one vote, we could head in here and we could say, let's make voting for a leader. Who's going to be the head honcho? Some people voted for Alice, some people voted for Bert. Let's make votes for Alice be 1s and votes for Bert's be 0s. We could do that, and then we could head over and we could go over here to data, attribute to matrix, except, we could do that if we could pick just one column. Just one column. But we're not interested in just one column. We are interested in 3 columns. We could put 1s and 0s in here for the 3 columns, but they don't mean the same as the 1s and 0s mean over here for the committees, where 0 means you're not on the committee. Here, a 0, say, doesn't just mean you didn't vote for Alice. It means you did vote for Bert. Come on back, Bert. So we can't use the affiliations command with these columns organized the way they are. Darn. What we need to do is we need to think about different ways of thinking about affiliations. For the leader vote, there's an affiliation that people might have to the event of voting for Alice. There's an affiliation people might have to the event of voting for Bert. Those are 2 different events, 2 different actions that you might be affiliated with. Okay, if you have 2 different actions for that, you want to have 2 different columns. So what are we going to do? We are going to go insert I don't know how to do this up at the top. I think I just want to go Alt-I-C. It's the only way I know how to do it because I'm old-fashioned. Okay, and that will insert a column. Alt-I-C, inserting another column there. We're going to have the same problem for billboard vote, of voting on, a new billboard law. Because voting no together is as meaningful as voting yes together. And we want the same thing for a streetlight vote. Voting no together is as important as voting yes together. Now that we have these spaces, what are we going to do? I'm going to copy this over here. K, Control C. I'm going to head over here to column L and do Control V. That's Control C for cut, Control V for paste. And now I have two depictions of the same information, but I'm going to give them different names. Vote for Alice, vote for Bert. And now for column K, I'm going to call up Control H, replace function, and I'm going to say Alice equals 1. Bert, voting for Bert is 0. And now in that column, I notice I have to rename this vote for Alice. That's fine. Here, this is saying, did you vote for Alice? In column K. Over in column L now, we're going to want to replace Bert's with 1s. And we're going to want to replace Alice's with 0s. And this is vote for Bert. Two different ideas, two different actions in the same event of voting. What's really tough about working with network data, but also really cool, is that the process of working with the data forces you to think really clearly about answering the question, what am I talking about here? What am I really meaning to measure? Because it should be symbolized in your data. Okay, I'm going to similarly copy information here for column M on the billboard vote, duplicate it, and the same thing for the streetlight vote. And I am going to, in my first column over here, I'm going to make yeses equal to 1s and no's equal to 0s. And I'm going to call that billboard yes. Then I'm going to go over to the duplicate, column N, and I am going to replace no's with 1s and yeses with 0s. Okay, and now I'm going to move over to the streetlight votes, and I'm going to call that billboard no. Always label your columns right away so you remember what you did. Because, I mean, look at all these 0s and 1s here. If you didn't have labels up at the top, you'd be lost. I know I would be. And believe me, I've been down that road where I've been working on a file, I come back 6 hours later and I have no idea what I did because I didn't label it. Label what you're doing. Okay, streetlight vote. This, and I've duplicated it here. We are going to make yes equal to 1 and no equal to 0. Great. And now that's going to be street light yes. And we are going to have street light. Whoops. I almost replaced things with street light no, but that's not what I want to do. I'm going to call it street light no, but we want to take our no's and make them 1s first. Always do things in order. And then yeses we're going to replace with 0s. Excellent. And now I'm going to turn that label into street light no. Now, and only now, do I have a set of data. 6 possible actions in 3 votes. Those are all forms of affiliation with an action now. So I'm going to head over. I'm going to load up what I had before, which was flcom. And I'm going to convert that now by heading over to the upper left and hitting paste. I now have how many? Yes, 1, 2, 3, 4, 5, 6 columns. And yes, they are opposites within these sets of 2. That looks good. Always double check. Make sure it looks like what you're wanting to have it. And I'm going to call this FL vote. And that is my dependent variable. It's the thing I want to explain. Oh, I'm getting excited. This is what I want to explain variation in. And my question really is a relational question. What leads to two people having the relationship of voting the same way? Is it that they're members of the same party? Is it that they're both men or both women, right? All these theories about, oh, women always, do the same thing together and men stick together. Is that true? What about if you share seats nearby? What about if you're similar in age? Or what about if you hang out together on a bunch of committees together and, you get kind of familiar and comfortable with each other? Do you end up voting the same way because they're people you feel comfortable and familiar with? And boy, in this case, it's an entirely fictional example, so, it's going to be a fictional result, but you could find out a real answer in just a week or two. It's going to be fun. Okay, let's save it. FL vote. And now, of course, we have to transform it, which means we're going to go to affiliations. Okay, and we are going to take FL vote, and we are going to look and compare rows. And then we're going to hit OK. Oh, sweet. Okay. Now we have the holy grail of QAP regression preparation, which is a set of matrices. Each one describes a unique variable, a unique idea, a different kind of relation. Each of those variables is a matrix. Each of those matrices describes the same people. And importantly, it describes them in the same order. Alice is always in column 1 and row 1. Kate is always in column 11 and row 11. Make sure you do this. If you have them in different order, it won't make sense. The computer will get confused and, it will be bad. Really bad. And you will call me up at 11:35 at night saying, Professor Cook, what's going on? And I'll have to take you step by step through it. And we'll make it work. But if you make sure to do that right from the get-go, you'll be pretty darn good. We're actually ready to run an analysis. It's a fictional analysis. Actually, it's a real analysis of fictional data. So I don't have any skin in this game, but, what do you think really matters? You could test some of these theories and some of your own, some ones that you have for politics or for something going online pretty soon. And this is your big assignment, right? And you can see it doesn't take long once you have that original data collected, and you've been collecting similar data already, right? It doesn't take long to work through and get it ready to go. Now, we're going to head over to test the tools, testing hypotheses, dyadic, QAP, MR QAP, which stands for multiple regression QAP, linear regression, and we're going to use the double-decker semi-partialing MR QAP because it is the best mode of permuting and assessing a statistical significance. Okay, it's a small detail you don't need to keep track of. There are going to be a number of random permutations of your matrices, 2,000 of them, and to make it really random, you can even put a random number in to generate some more random numbers, because in a computer all numbers are pseudo-random. What's our dependent variable? Oh, goodness. Okay, we want that to be FL vote, row F, the transformation of FL vote. And then we want to take a look at independent variables. These are going to be FL party, same party. The next one was FL sex, same sex. FL seat, absdiff seat, absolute difference in seat number. FL birth year. You notice it's just adding these in every time I hit these ellipses. And notice I wrote these down on a sheet of paper, and now I can just go straight through, and I know I'm not missing any because I wrote them all down. The last one is FL COM, row F. Now, I'm going to take one last look at these, make sure I got the transformed matrices, the ones that start with 2 mode and turn them into 1 mode data. I have 1 mode data. I think I'm good. Optional partition. I don't want to do an optional partition. I'm going to have 3 outputs. Predicted values, model fit statistics, and coefficients. Okay. You ready? I think I'm ready. I'm going to hit OK. And it's going to take me a little while to run. This one won't take too long because it's a small network. But if you have a large network, and you really shouldn't have too large a network because you don't want to have too much work for yourself, it will take a little while to chug through this, especially if you have an older computer. If you really have an old computer, your computer might choke on this because it involves running 2,000 analyses. So, what are 2 things you could do? You could cut down the number of random permutations to 1,000 or 500 even. The second thing you could do is you could go into one of the computer labs in Augusta, Bangor, and there's one in Rockland that has UCINET on it. Bring your files and work with those. I'm going to hit OK now. Oh, that didn't take too long. I have a nice computer. And it is going to tell me what I've got here. It has, p-values. It has unstandardized coefficients. Those are your slopes. You notice the p-values are also the same as large. When we went through and described, we're going to in a minute. We're going to describe statistical significance. We're going to talk about what it means to have a p-value. There's a cutoff level of 0.05, and it is meaningful. If you have a p-value of 0.05 or less, then that means that you have only a 5% or less chance, just multiply it by 100 for your percent chance, of this big a result, your slope over here, of occurring that hugely by chance alone. You want small p-values. P-values of 0.05 or less indicate statistical significance, indicate that you can trust what's going on because your p-value means it doesn't happen very often at all by chance alone. Chances are really good. 95 out of 100, as a matter of fact, which is the converse of 0.05. 95 times out of 100, randomly speaking, you wouldn't get a result that big. Only a 5% chance of you being wrong by chance. You also have an R-square here. Remember R-square from last week? You multiply it by 100, and it is the percent of the variation in voting that is explained by all of these variables together. It explains 35.8% of it, which is pretty good for a fictional data set. Actually in social sciences, right, that would be awful in physics, but these are people here explaining 35.8% of the variation in how people behave is pretty darn good. That's fairly predictable. We see a few things over here. A lot of p-values that are pretty high. Birth year comes close to being significant, but no, there's only one that is really significant here, and that is the result for same party. So we can interpret that slope. And what does it say? It tells us, that when same party equals 1, we are going to multiply that 1 times 1.19365 and add it to the number of in the cell for vote, which is the number of votes that you voted the same way. people in the same party vote the same way a little bit, 1.2 times more often than those who are not of the same party. Because when you're not of the same party, that's a 0. And 0 times 1.19365 is 0. 1 times 1.19365 equals 1. So the latter is 1.19365 bigger than the former. Okay, so we know now in this fictional example that people of the same party share one more common vote than people of different parties. That is our interpretation. That's our outcome. And we explain a significant portion of the variation in how often people vote together, just with party alone. Men and women don't seem to, statistically speaking, significantly speaking, they don't seem to be really more inclined to vote together or not. Whether you sit next to someone doesn't really matter. We have to say that because there's a significant chance that by chance alone we'd get a result like this. And birth year. No, that doesn't seem to work for us. There's not a p-value of 0.05. Even committees, being on committees together, doesn't seem to matter as much. Okay, if there is a p-value of larger than 0.05, forget it. It's not a big enough effect for you to be able to trust. Now, we're going to need to talk about what that means in just a little bit. In fact, let's head back over and run through an example. We started with a fictional legislature. You now have some results, some with small p-values and some with large p-values. Why is a large p-value bad? Let's start from that slide and keep going. Well, we ran a QAP on our fictitious data. That's lovely. And here's the screen to help you through it if you need it. Okay. Oh, apparently I've been hiding slides. I don't want to hide slides. I'm going to unhide them and we'll get right back started from the current slide. How will we test for statistical significance? Well, see, the reason we need to do that is that even if you have some absolutely random matrices, some slope coefficients are going to show up anyways. Why? Because sometimes just randomly things line up from one matrix to another. Let me show you what I mean. We're going to go back to UCINET and I'm going to show you right now how that works. I'm going to give you some non-zero slope coefficients. In a world in which everything really is random, we're going to have the computer tell us, no, there's some relationships between variables. That's not so. So how am I going to do that? Well, I'm going to head over to UCINET, and I'm going to create 2 random graphs. They're going to have 12 nodes in them. Okay, and this is going to be graph 1, random QAP 1. There we go, RQ1. And I'll create that. RQ1. And now let's create a second one. Random. And I'm going to make this become RQ2. Okay, now I'm going to head through and I'm going to create a third one. Random graph here. It's going to be called RQ3. Okay. And now I'm going to head over to Tools, Testing Hypotheses. Now, I just did this. I don't know exactly what numbers are going to turn up. I'm going to run an MRQAP, although those of you who are statistically minded, knowing that there are zeros and ones, I should do a logistic regression, but the point will still hold here. Double-decker semi-partialing QAP. We're going to run something new. It is QAP random or random QAP. Random QAP 1, And oh, now I want to go through. What do I do when I have junk here? I run through, I select it, and I hit delete. Now I'm going to find random QAP 2 and random QAP 3. And these, you saw, I just randomly generated these. This is data that is not only fictional, but it is randomly generated. It's noise. It's static. There's nothing systematic going on here at all. And yet, when I run a regression, I get unstandardized coefficients here that are not 0. And I even have a p-value here that's 0.09, indicating that I would only get a number that big. Oh, just 9% of the time, 9.195% of the time if I multiply that p-value times 0. I would only get, right? So wow, that's really important to know. It's telling me that sometimes randomly I'll get a big number here. And sometimes, I'll get an R squared of 0.03. I'm explaining 3% of the variance in nothing, in particular, with some other random junk. Just randomly speaking, any variable will explain a little bit of what's going on with another variable. Okay. And in fact, if I ran this 10 times with 2 variables, just once out of chance alone, right? 10 times 2 variables equals 20 independent variables. I would surpass that p-value of 0.05. 5% of the time, 1 out of 20 times, I'd get, something telling me that it was something significant going on. That's a little scary, but I'm willing to live with that as long as I'm not including 20 variables in my test. As long as I just have a few, then I can live with that level of risk. But this is junk, and yet it's showing me that there's some kind of slope. So we have to have a standard. What do? We have to run a test that says, gosh, how do we figure out that p-value? That p-value is a claim at saying, hey, this number this big, only 9.195% of the time is it going to be that far away from 0, that big. Well, how do I know that? How could you know that? The answer is cool. The answer is that you essentially do this procedure that we just did. You generate some random information and you run a regression based on it, and you see how big the numbers in your random regression are, and you compare them to the real one. And if those random numbers often get as big as your real numbers, then maybe your real numbers aren't real trustworthy. But if those random numbers generated very rarely get as big as your actual numbers that you get in your test results, then that means that the bigness of that slope, the bigness of the effect of your independent variable on your dependent variable, which you interpret just like in any other regression, that's got a good fighting chance of being something real going on there. That's what statistical significance is all about. It's about comparing random noise to reality. How would we do that? What's really cool about QAP regression is that it does it in a very practical way. I've just shown you step number 1, what we do to test for statistical significance. The first step is just to realize you could have gotten these results by chance alone. Number 2, then, the key is to figure out how likely that is. You have to figure out how to get a p-value that tells you how likely that is. Okay, and we would have rejected, by the way, both of those random junk slope coefficients, the unstandardized slope coefficients, because they both have a p-value that is bigger than 0.05. So we have to figure out how likely it is that our slopes are chance alone or not. Is the chance 5% or less, or 5% or greater? What you do is you calculate. This is the solution, step 3. You have to calculate how often you'd get results that big as the ones you got by chance alone by actually allowing for chance. And if by chance alone you get results as big as you got, but that is very, very rare, okay, very, very rare that you get results that big, then you can trust them to not be due to chance, but reflecting some real trend. Let me say that again because it's so important. If by chance alone, okay, and I'm going to show you how to simulate chance alone, the computer will do it for us. If by chance alone, the results that you get are very rarely as big as the ones you got from real data, then you can trust that real data effect is not due to chance. And you can reflect, you can be trusting that that is some kind of real trend that's going on. How do you do that? How do you figure out what numbers would show up by chance alone? You do something random. In QAP regression, quadratic assignment procedure regression, you randomly permute the rows and columns of the dependent variable matrix. Okay. What does that mean? You switch the rows and columns around. That's literally what you do. You randomly switch the rows and the columns in the matrix. And then you treat it as if it was somehow meaningful, and you run a regression after you've turned it into junk, after you've turned it into noise. And after you've turned it into junk and noise, randomly speaking, you see what kind of effect you get. And then you ask yourself, excuse me, I think I need to plug in. You ask yourself, how likely is it that I'm going to get that kind of result? The answer is, well, how often does it happen to you that you get a result as big as you got with your real data when you junk your data up? If when you junk your data up, you get just as big a result all the time, then, you probably shouldn't trust it. So if, on the other hand, random results as big as your original data's results happen less than 5% of the time, then you can trust it. So QAP regression actually does a very cool thing of running your regression, but with the rows and columns in your matrix messed up hundreds and hundreds of times, or thousands of times if you want. And that is going to give you statistical significance. Let me show you, because I know this is confusing. You're not going to be tested on it. You're just going to have to run this model and think about, very carefully, coming back to this video a few times, about what statistical significance means. It means you can trust the result. Let's take a look at the original matrix. Okay? Now this is a part of it. Simplifying it down to just 5 people. Alice, Bert, Carl, Donna, and Earl in our fictional legislature. If we take that original and we switch the rows and columns around, and by the way, whenever you switch a row and a column, well, whenever you switch 2 rows, you switch the 2 columns the same way. So randomly permuted, I ran that through, by the way. You can get UCINET to randomly permute just once, and that is in the, let's take a look, data permute command. Okay, we're going to head back, go from current slides. I allowed it to randomly permute. It took Alice and it moved Alice over to the 2nd row. Then it took Bert and it moved Bert over to the 5th row. And then it took Earl from the 5th row and moved Earl over to the 1st row. It randomly kept Carl and Donna just where they were. And it did the same things, the same order of switching for Earl and Alice and Bert in the rows as it did in the columns. Okay. you'll notice the data in the matrix is the same. Earl is still in the same party as Alice. This is party information, this matrix, and is in the same party as Carl. But now we're going to do something devilish, which is that we're going to take the labels from the original and slap them onto the Bermuda matrix. So now it looks like Alice, Bert, and Carl are in the same party. That's not true. It's false. It's fake. It's noise. It's junk. It's random. And it's randomly done over and over and over again, thousands of times, switching in various combinations. And you can imagine if you have, say, 50 nodes, there are lots of different ways you could do that switching. You create junk, and then you find out if you get slopes as big, indicating what kind of effect you have. Do you get a slope as big with junk? And if you did it 100 times, would you get slopes as big with junk? Would you get them that big 5 times or more? Well then, no, we're not going to trust that result. If you don't get slopes as big as what you got with your real data when you use junk, then, hey, we're going to trust that data then. We're going to trust the result is real and significant and meaningful. Okay? And so that is a description of how to work with fictitious data, albeit, but how to start with a table of regular old individual level information, individual's party, individual's sex, individuals belonging to committees, individuals' votes, how to turn that into network data, and how to run a regression that results in slope coefficients, which from last week you should feel comfortable interpreting the meaning of. Now on top of that, you should also be able to take a look at p-values and be able to conclude, am I going to trust this junk? Sometimes no, in the case of randomness. But sometimes when you have something real, you'll have a p-value that's really low. And that means the probability that this is junk is low. And that means you can trust the result. You now have all the information and all the capabilities necessary to start your work on your final project. I wish you lots of luck, and please be in touch if you end up getting confused along the way or feeling that you're not sure you're doing the right thing. I'd love to help. Thanks again, and have a good night.